Alright, sorry I can't be there today. Henry is sick, so I'm going to have to be home with him, so I'm making this video for you guys so that hopefully we can go through these notes, and you'll still be able to keep on track with our plan for the week. So today we're going to talk about trigonometry and polar coordinates. And polar coordinates are pretty cool. They have a lot of uses. We're not going to have enough time to get into a lot of those, but there are a lot of things that they can actually be used for in the real world. Here, Mr. Passwater sort of starts off, he is talking about traveling. And if you think about different ways to travel, you could walk, bike, drive, fly, boat, etc. And each method has its advantages and disadvantages. For example, if you are driving from one location to another, you have to stay on the roads, which are generally formed by a rectangular grid system, particularly if you're talking about like in a city square. Usually all of the roads sort of form like a grid system. Not necessarily so true whenever you're out more where we live, but definitely in like a city sort of system, that's going to happen a lot more. However, if you're flying or on a boat, then you don't have to follow the road system. You just go directly to where your destination is. And that is sort of what we're going to see with polar coordinates. So whenever you're plotting rectangular coordinates are just the normal coordinates that you have used for pretty much all of your graphing, all of your mathematical career thus far. And it's your x, y coordinates. You have an x-axis and a y-axis. You use an ordered pair, x, y, to describe them. These are also sometimes called the Cartesian coordinates there. So that word right there, Cartesian, something you might see, but typically they'll use rectangular instead. And you basically, your x coordinate tells you how far to go right or left, and your y coordinate tells you how far to go up or down. Another way we can think about telling somebody how to get somewhere on a coordinate plane is with a polar system. And with the polar system, we do not use x and y coordinates to define. It's much more like flying an airplane. And if you're going to fly an airplane, you just point to where you're going to go and fly a certain distance. And so this is going to need, you'll need the angle of where you need to go in standard position and how far that is away from the origin, which is going to be your radius. So it's kind of interesting. So normally, if we were going to graph this point, let's see if they'll let me draw. If we were going to graph this point, come on, let me draw. It doesn't want to let me draw on that picture. Hold on. Okay, now I think it's working. So if we want to graph this point, so far what we would have done is we would have had an x coordinate right here, and we would have a y coordinate, and we would just go to the right x coordinates and or x units, and we go up y units, and that would give us the location of this point. But with polar coordinates, we are going to use an r theta system. R is going to be our radius, and theta is going to be the angle of where we're going to. So rather than going left or right first and then up or down, basically you can only move left or right, up or down, we are going to set our angle. So if this angle right here was pi over 4, we would set our angle to pi over 4, and our radius would tell us how far to go. So that radius would be, if it was 7, we would set our angle to pi over 4, and we would travel 7 away, and that would get us to that point right there. The absolute value of r represents the radius, but this letter r right here, we could call like a signed radius, because you can have positive and negative radii, and we'll see what that looks like here in a second. One thing about polar coordinates is the same point can be represented in many different ways. We already know, as far as angles and standard position go, that for example, this angle right here would be 0 radians, but it could also be described as 2 pi radians or 4 pi. So there's going to be many options for that. Here, so let's get into seeing how to graph here. So this is what a polar coordinate system is going to look like. And one thing you need to know about this is the axes are still counted that same way. So if you think about it, like here is, so let me draw. This is 1, 2, 3, 4, 5, 6. That continue on. This is 1, 2, 3. But rather than having a grid system where we just have all of these rectangles all over the circle, all over the graph, we have circles. So our first major circle that we have right here has a radius of 1. And then if you go out further, you have a radius of 2, and then a radius of 3, and then they have intermediate ones in here. And this is basically the unit circle here as far as our degrees go around. Do be careful because this line right here and this line right here are not drawn in on our unit circle. Typically, pi over 6, pi over 4, and pi over 3 are. This would be pi over 12, and then this one up here, it'll let me scroll up here, would be 5 pi over 12. Typically, they're not going to give us those values to deal with. Each one of these goes up by pi over 12, 1 pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12, 6 pi over 12, etc. They're usually just going to give us unit circle values. Just be careful not to count this first one right here as pi over 6. So if we are plotting our points here that they have asked us to plot, and let me zoom out just a little bit so it'll all fit in one frame. If we were plotting these points, this is how it will work. So when, oh gracious me, when we see that we're going to plot point A here, it is 2 pi over 3. So I like to think about my, oh gracious, why is it doing that? I like to think about my angle first. So the first angle we're looking at is at pi over 3. So pi over 3 is going to be this angle right here. And I'm actually going to continue that line right there all the way across. And then whenever we graph our point for A here, we're going to start at what we would normally call the origin. I believe for polar coordinates, this point right here is not called your origin anymore. It's called the pole, or at least I think I've heard that. And so we either go towards the angle that we are trying to reach, or we go away from that angle. If we go towards the angle that we are given, then that's going to be a positive radius value. And if we go away from the angle that's given, it's going to be a negative radius value. And we'll see that whenever we get to some of the next problems. But I think these all have positive radii. So if we go over here, we got pi over 3. It's on this section. And we're just going to count out for the circles. Here is our circle where we have a radius of 1. And here is our circle where we have a radius of 2. And so that gives us the point right here. Okay, and so that will be our point A. We need to label that there. Let's use a different color for the next one. So let me change my highlighter here. Let's use green for this. And let's go and make it a little bit smaller. So it's not so thick. All right, and so our next one is 3 pi over 2. And 3 pi over 2 on our unit circle is right here. That's what we would be going towards. I'm going to go ahead and extend that all the way across, but keep in mind the angle that we're going towards is down here, 3 pi over 2. And if we want a radius of 1, we'll start right there at the pole, and we're just going to go out till we hit the circle that has a radius of 1. That is right here, and this would be our point B. So there's point B. For point C, let's use a different color on the highlighter again. Let's go to pink on this one. And for C, we're going to 4 pi over 3. 4 pi over 3 actually goes right here. So I'm kind of going over what I've already had. 4 pi over 3 is over here. Sorry, I can't write as good on this laptop as I can my school computer. So this 4 pi over 3, we're going towards 4 pi over 3 until we get to the circle that has a radius of 3. That's always all the way to the outside right here. Let me use a different color so that shows up. Let's use purple. Right here. So that would be our point C. And then we've got negative pi over 6 on our unit circle. That negative pi over 6 is right here. Right along that line right there. Do be careful on this. Pi over 6 is not here. Remember, those are our pi over 12s right there that don't show up on our unit circle. So right here, this is pi, or negative pi over 6. And if we have a radius of 2, that means we're going to go out till we get to the circle that has a radius of 2. And that point would be right here. So there is point D. So we have all 4 of our points graphed on that those polar coordinates there. So let's continue on with a little more practice. Let's see what it looks like. Down here, we're going to see on this last one, at least, we're going to see a negative radius, which is going to be a little bit different. So if I'm going to graph these points, I've got, gracious. Okay, if I'm going to graph these points for A, I've got pi over 4, which is right here. And I want a radius of 2, so I'm going to go out 1, 2 right here. And point A would end up right here on my polar coordinate graph right here. Point B, notice right here, I've got negative 7 pi over 4. Now, 7 pi over 4 is typically right here. On my unit circle, right there. But I have negative 7 pi over 4. So that means normally 7 pi over 4 would go all the way around this way. Negative 7 pi over 4 is going to be in the opposite direction. So I'm going to go around that same distance over here. You might need to do negative 7 pi over 4 plus 2 pi, which is 2 pi over 1. You could get common denominators there. That's going to be 7 pi over 4 plus 8 pi over 4 if you get common denominators, and that will give you pi over 4. So negative 7 pi over 4 is the same as positive pi over 4. And I have a radius of 2. Now, look what's happening right here. I'm ending up at the same spot as I was for A. Okay, so I've got negative 7 pi over 4 is the same as pi over 4, and my radius is the same. So this point is A, but it is also B. The next point we have is 9 pi over 4. 9 pi over 4 is not on our unit circle. So let's subtract 2 pi to see where that ends up. So I've got 9 pi over 4. And I'm going to subtract my 2 pi, which is like 2 pi over 1. You got to get common denominators. So that would give us 9 pi over 4 minus 8 pi. And you might see what's going to happen here. 8 pi. Over 4, and that is going to equal, again, pi over 4. So you have a radius here of 2, and again, pi over 4. So not only is it A and B, but it is also C. And we can look at this last one here, and I wonder if he's done the same thing. I bet he has. For the last one, we've got 5 pi over 4. And so this will get us into having a negative radius. So 5 pi over 4 on your unit circle is over here. Right here is 5 pi over 4. That's this right here. And I'm going to highlight 5 pi over 4 here. Let's use the yellow. 5 pi over 4. Gracious. 5 pi over 4 is right here. But earlier, I was highlighting all the way across. And that's important because if I had 2 positive 5 pi, or positive 2, 5 pi over 4, I would go right here, and that would be my point. But when I have a negative radius, I'm going to start at the pole right here, and I need to go away from that angle in the opposite direction. So I would go 1, 2 right here. So what we're seeing here is that really that one single point right there that is on our graph could be A, B, C, or D. All of those points end up at that same point on the graph right there. All right, let's move on. Okay, again, he says here that illustrates that all of those polar coordinates can be given in different ways. In fact, there's actually infinitely many ways you can use polar coordinates. So, if we go over here, this one says to plot the point with polar coordinates 5 pi over 6, 3 on the polar grid above. Then write the polar coordinates for the point 2 different ways. So let's graph this point first. I'm going to highlight 5 pi over 6 on my graph. 5 pi over 6 is right here, but let's go all the way across right here. So, and I'm going to label that point, or that right there, as 5 pi. Come on. Over 6. So that is where 5 pi over 6 falls there. And I have a radius of 3, so I'm going to start at the pole right here, and I'm going to go towards the angle. And so this point would end up right here. That's the point that we have graphed. Now, there are infinite ways that we can describe this because, first of all, 5 pi over 6 could be given as a different angle. So one way that we can write this differently is we could do, for this point, instead of 5 pi over 6, we could go one more full rotation. So if we do 5 pi over 6 and we add 2 pi to it, that's like 2 pi over 1. So that would be 5 pi over 6 plus 12 pi over 6 to get those common denominators. And that would give us 17 pi over 6. So another way we can write this point right here is we could call it 3 17 pi over 6 here. Now, we also could subtract 2 pi, or we could add 2 pi 3 times, or we could add 2 pi 10 times. You could have an infinite number of coterminal angles that you could use right here in place of that 5 pi over 6. Another option that you can have for this is to use a negative angle. So right over here, across from 5 pi over 6, this is 11 pi over 6 right here. So if we use the angle 11 pi over 6 right here, whenever we graph, if we want to still get to the same point that we've graphed over here, but we want to use the angle as 11 pi over 6, what we want to do is we want to go away from 11 pi over 6, not towards 11 pi over 6. So we would use 11 pi over 6, but we would put a -3 right here for that point. And then, so these are two different points we could use, but there are infinite points that we could really use for this particular point, because we could give coterminal angles for any of our +3 5 pi over 6's. We could also do coterminal angles for 11 pi over 6 for this -3 right here. So there's just so many ways you can write polar coordinates. Okay. Now, what I'd like to do next is connect what the rectangular and the polar coordinate systems look like. And I know we aren't allowed to use Desmos on our exam, but I would like to look at Desmos really quickly, just to point out a couple things about this. So, if you go to Desmos and you just graph a point, like the regular old 0.23 right here, for that, it's just going to graph 2, 3. It just shows up right here. However, I can go to graph settings over here, and you'll notice there's an option right here to do this. You may have used this a little bit whenever you were in Math 3 to kind of like cheat on the unit circle problems on the Desmos on your exam. We don't do polar coordinates in Math 3, but you may have used this to kind of remember things about the unit circle on Desmos there. But notice that point right there did not move. If I change this back to the grid, it looks like this. If I change it to polar coordinates, it's going to look like this. So if I were going to use polar coordinates for this, my angle is somewhere between pi over 4 and pi over 3. You know, we'd have to get an estimate there. It's not going to be right on the grid lines. And my radius is somewhere between 3 and 4, probably like a 3.6 or so right here. So I could use either rectangular coordinates, which would just be 2, 3, or polar coordinates to describe that same point right there. The only thing that's changing whenever you do that is what the background looks like. In this picture that he's got here, he's reminding us to graph polar coordinates. We just go to the right x, up y, if both of our x and y's are positive. Whereas for the polar coordinates, we would go a certain angle, we would turn a certain angle and go a certain distance, which is our radius, in that direction. So if you put these two pictures together, there's two ways we can define point A. We could either call it x, y, or we could call it r, theta. And there are equivalent forms of that. So, if we go on down, here, using that picture, if we want to use trig, we can kind of set up what he gives us here. Uh-oh. Didn't mean to downsize that. So if we're thinking about this angle right here, we could find sine or cosine of that angle. If we did cosine, I'm going to write it over here, cosine of theta, that would be our opposite over our hypotenuse. No, it wouldn't. That'd be sine. Hold on. Cosine would be adjacent over hypotenuse. And for an angle in standard position, that would be x over r. So notice that we've got that set up over here. And then for sine, in a similar fashion, if we have sine of theta, that would be opposite over hypotenuse. And opposite over hypotenuse for this picture would be y over r. And we have this set up right here as well. So if you wanted these equations solved for x and y instead of sine and cosine like they are, all you would have to do is just multiply both sides by r right here. It would cancel out the r here, and you'd multiply by r here. That will give you x equals r cosine theta. And then same thing over here. We could multiply by r and multiply by r, and we would get y equals r sine theta. So these two formulas right here can be used to convert polar coordinates to, polar coordinates to rectangular coordinates. So let's look at what that looks like here with some examples. If I have 2 pi, then I would, in this case, want to say x equals the radius times cosine of my angle, which is pi. And they'll be giving us things that are on the unit circle. So the cosine of pi, when we're thinking about that unit circle, is going to be -1. And so we'll get -2 right there. And then if we go to y, we would have 2 sine of pi. And that would be 2 times sine of pi is just a 0. So we would get 0. So our rectangular coordinates for this point would be -2, 0. Let's flip over to Desmos just to look at this. It's good to think about what the graph looks like for this. So Desmos will only graph rectangular coordinates. So we have to graph our -2, 0. Or at least as far as I know, it will only do that. -2, 0. Oh my. So that is this point right here. And we can see it graphed. If we change our background to the polar coordinates, notice that we are at pi is our angle, and we have a radius of 2. So that should kind of make sense there. All right, let's do another one. If we want to do b, which is 5 pi over 3, 4, we would do x equals 4 cosine of 5 pi over 3. And that is going to be 4, and then we'll need to think about our unit circle at 5 pi over 3, and 5 pi over 3 is there in the 4th quadrant, and let's see, cosine is going to be 1/2 there. So for our x coordinate, we'll get 2, and then our y coordinate, we're going to have 4 sine of 5 pi over 3. Come on. And that is going to be 4 times square root of 3 over 2. And that 4 is like 4 over 1. The 4 and the 2 can reduce, and we will get 2 square root of 3 there. So I'm kind of running out of room. This point right here could be written with an x coordinate of 2 and a, in the 4th quadrant, sine is negative, so that should be negative. This should be -2 square root of 3. And so if we look at that on Desmos just to check, I've got 2, -2 square root of 3. So if I graph that, 2, -2 square root of 3, you can see in polar coordinates, you go to the right 2, you go down 2 square root of 3, which is about 3.5. But if we change our background to our polar graph, notice we're right there on the 5 pi over 3 line, and we have a radius of 4, which is what our point was whenever we had it in polar form. Okay, if we do one more for C, we'll just have x equals, just use the coordinates as they're given. So if the radius is -3, put a -3 right here. And then we would have cosine of 7 pi over 6. And 7 pi over 6 is in the 4th quadrant and 3rd quadrant. Everything is negative there, or all your sine and cosines are negative there. Cosine is going to be -1/2. No, negative square root of 3 over 2. There, which is going to give you a positive 3 square root of 3 over 2 for your x coordinate. For your y, you're going to have negative 3 sine of 7 pi over 6. Sorry, this isn't going to write very well. Which is going to be negative 3 sine, oh, not sine. Let me write that sine right there. Sine of 7 pi over 6 is going to be negative 1/2. And that is going to be 3/2. It won't let me write there. There we go. So this point right here would be 3 square root of 3 over 2 and 3/2. Again, it's really helpful to graph those, and it's just kind of hard for me to graph if I don't have polar coordinates. So I'm going to show you what it looks like over here again on Desmos. You're welcome to use this to kind of help you along as you work on these. So we got 3 square root of 3 over 2 and 3/2. So 3 square root of 3 over 2 and 3/2 there. And so whenever you type that in, it's graphing the polar coordinates. Oops. It's graphing this right here. 3/2 is just 1/2. You can see the y coordinate right there is 1/2. 3 square root of 3 over 2 is a little more than 2/2, so it's right here. That's just going over and up, but if you change it to polar coordinates, this was supposed to be, what was it? Negative 3, 7 pi over 6. So if you look, 7 pi over 6 is right here, but you don't go towards 7 pi over 6. You go away from 7 pi over 6 out 1, 2, 3, and so that gives us the correct point right here. So it's always good to graph these and kind of think about what they look like for that. That is what we're going to do for going from our polar coordinates to our rectangular coordinates. We are also going to be asked to convert our rectangular coordinates to polar coordinates. So if we're thinking about this picture right here, and we think about the scenario where we're given x and y, it's going to be very easy to find r, because all we're going to do is use the Pythagorean theorem. X squared plus y squared is going to equal our r squared. Using trig, we also know that tangent of theta is going to be y over x, which can be used to find the value of our angle. So we're going to use this information to find the value of that angle. It's a good idea, he notes here, to always sketch this point out first. That way you can tell if your answer makes sense. So let's look at example 5 here. We got the point negative 2, 2. And so if we think about graphing that, just negative 2 up 2, it's going to be in the second quadrant right here. So you already can kind of get a picture of what that's going to look like on a polar graph. You should be in the second quadrant, so you're looking at angles that fall here somewhere in that second quadrant, and then you're going to have a radius there that's going to be more than 2 for sure, but not a lot more than 2. So to find your radius, you're just going to do a squared plus b squared equals c squared. So you can use the negatives if you want, because whenever you use the negatives, you're going to have negative 2 squared plus 2 squared is going to equal, I'm going to call it radius squared here. And you can use the negative or not. It doesn't matter, because when you square these, you're going to get positive. So you'll get 4 plus 4 equals r squared. That's going to be 8 equals r squared, and then you will square root both sides. There is a good chance right there they're going to break down that 8 right there into the square root of 4 times 2, which means that you're going to get 2 times the square root of 2 as your radius. The other part of this that you're going to have to do is you're going to have to figure out what that angle is. So the angle that you're looking for is really this angle right here. You're really looking for this angle right here on that. So we know that tangent good gracious. Oh, I can't write with this. Alright, tangent of theta should equal y, which is 2. Come on. Over x, which is negative 2. Let's see. It'll let me. There we go. Finally got that. So kind of running out of room here. Sorry, it's hard to write on the screen right here. Just move this down. So if that means that we're looking for where tangent of theta, gracious, is going to equal negative 1. And keep in mind in which quadrant you're in. You're in that second quadrant. So there in that second quadrant, that angle is going to be 3 pi over 4. So in rectangular coordinates, I've got negative 2 over 2. In polar coordinates, I'm going to have 2 square root of 2 and 3 pi over 4 for that. So that'll be my answer for part A. If we think about B, if you think about graphing that, you've got 1 negative square root of 3. So if we just graph, well, we got an x coordinate of 1 and a y coordinate of negative square root of 3, which is somewhere between 1 and 2. So we're looking at about right here on our graph. So we will be in the 4th quadrant there. So when we're thinking about angles here, we're thinking about going, I didn't quite draw that right. We're thinking about going from 0 all the way around here. So we're thinking about that angle. Sorry, this is really not writing very well for me here. So just Pythagorean theorem for our radius. So we do 1 squared plus negative square root of 3 squared equals our radius squared. And so 1 squared obviously is just 1. Negative square root of 3 squared, the negative is going to go away when you square it. Squaring a square root is just going to cancel each other out. You'll just get a 3 right there. That's going to equal our radius. And we'll get 4 equals our radius. And we can take the square root on our radius squared. Sorry, that should still be squared. We'll square root both sides and we'll get 2 for our radius there. So our R coordinate is going to be 2. Then we need to think about tangent. So tangent of theta is going to be y over x, so negative square root of 3 over 1. So basically we're just looking for where tangent equals negative square root of 3. We got to think on that unit circle. We're in the fourth quadrant, so it's either going to be at 11 pi over 6 or at 5 pi over 3. So you kind of got to think about those points there. And you're looking for where your y is bigger than your x, which is going to happen at 5 pi over 3 if you check that point. And so our angle right there is going to be 5 pi over 3. So those coordinates right there are going to be 2, 5 pi over 3 for that one. Okay, and for the last one here, we've got 0, negative 5. And so if we think of graphing that point 0, negative 5, that is going to be right here on the axis. And this one you really don't have to set up very much because the radius right there is going to be 5 because it's just a vertical line. You don't really have a triangle in this case. And then your angle, we can see pretty clearly, is going to be your theta is going to be 3 pi over 2. So a lot of times if you get these that end up on the x or the y axis, they're a little bit easier to do. So the coordinates here would be 5, 3 pi over 2 for that. And of course we could always do something different with our angles or maybe use a negative value right here. But this would be your most common answer to get. All right, we've got one more thing that we have to cover here, and that is complex numbers. So it says previously we have written complex numbers using the form a plus bi. So we looked at this some back, I think it was in Unit 2. And a and b would be constants. Something we have not done is we have not graphed complex numbers. So a complex number can be understood as a point in the complex plane, and we can be determined by its corresponding rectangular coordinates. So when the complex number has the rectangular coordinates a, b, it can be expressed a plus b, I. So it's, in this case, it's like, for example, this point right here is 3, 2. And 3, 2 is like 3 plus 2i. So this axis right here, instead of being your x-axis, it's your real number axis. And then up here, instead of being your y-axis, it's your imaginary axis. So we have already learned that x equals r cosine theta and y equals r sine theta. So we can still use these with complex numbers. But when we have complex numbers, r theta can be written as r cosine theta plus I times r sine theta. Basically what you're doing is instead of having x plus I times y, you're replacing x with r cosine theta and y with r sine theta there. So let's look at a couple examples here. So a complex number is represented by a point in the complex plane. The complex number has the rectangular coordinates -2, -2. What is one way to express the complex number using its polar coordinates? So if we wanted to use the polar coordinates here, we'd first just convert to polar coordinates. So to do that, we need the r and the theta for that. So to get the r, we're just doing Pythagorean theorem, right? We've already pretty much done this one. So we got -2 squared plus -2 squared is going to equal our radius squared. And so that is just 4 plus 4, which is 8 for our radius squared. And then we would, of course, square root both sides. That square root of 8 can be written as 2 square root of 2 for our radius. And for our angle, we're going to think about graphing this. And so if we're at -2, -2, we're in that fourth quadrant right there. And our tangent of theta for this would equal y over x. So that'd be -2 over -2. So we're thinking about where tangent is going to equal 1, because -2 over -2 is going to give us 1. And so that is going to happen right here in that fourth quadrant at 5 pi over 4. So if I want to use this form right here to represent my if I want to use this form right here to represent my complex number, I could use my radius, which is 2 square root of 2, and then cosine of theta. Well, actually, instead of theta, let's go ahead and put in our angle we found for theta. Cosine of 5 pi over 4, plus I, good gracious, times sine, times 2, good gracious, square root of 2 sorry, this is really not writing well over here on the edge of my computer screen. Gracious me. Sorry, guys. We got 2 square root 2, and that'll have sine. It's like it's giving out on me. Got one more to go. Of 5 pi over 4. That's a 5 pi over 4. Sorry, it's terrible writing here. And so we could write it like this. This last question that he gives us here tells us that a complex number is represented by a point in the complex plane. Using polar coordinates, the complex number can be expressed as 4 cosine of 7 pi over 6 plus I 4 sine of 7 pi over 6. Express the complex number using its rectangular coordinates. So whenever we're doing this part right here is your x, and this part right here is your y. So all you have to do is evaluate that. Your x is going to equal 4 times cosine of 7 pi over 6. 7 pi over 6 is in that third quadrant, and your cosine there is going to be negative square root of 3 over 2. If you multiply those together, that 4 can be over 1. You will get x equals negative 2 square root of 3 as your x coordinate. And then your y coordinate right here is going to be 4 times sine of 7 pi over 3 is going to be negative 1/2. I'm sorry, 7 pi over 6, not 7 pi over 3. And so y is going to be negative 2. And so your rectangular coordinates for this complex number is going to be negative 2 square root of 3 and negative 2. So, sorry for such a long video, and sorry that I can't be there today. But hopefully this will be enough for you to be able to do your assignment that goes with these problems. Do your best on it. Hopefully I will be there tomorrow, and we can go back over anything that maybe is a little bit confusing to you.